So I'm going to start the seminar. Hello, everyone. Welcome to the Friday seminar series, also called a Colloquia of the Center for Earthquake Research and Information at the University of Memphis. I am Arif, today's host, a third-year PhD student here. The objective of this seminar series is familiarizing us with the research work of the people from geophysics and similar disciplines. And now, please allow me to introduce you all with our today's speaker, Dr. Chris Morley. Dr. Morley holds a PhD in geology with a focus in structural geology. He began his academic career in Kingston University in the UK as a lecturer. Later, he worked in the University of Brunei Darussalam in Brunei, University of Aberdeen in Scotland, Chulalongkorn and Chiang University in Thailand, and finally, he retired from the Petroleum Geophysics Master's Program at the Chiang University as a professor in 2019. Besides his 17 years of academic career, he also worked in oil industry for 21 years, where he began as an exploration geologist for Amoco in Houston. In 1985, he also worked in the research lab of Elf Aquitaine in France as a structural geologist and retired from PTT Exploration and Production in Thailand as a senior geophysicist in 2022. His over 40 years of extensive experience in structural geology has been mostly focused on the tectonics and deformation within sedimentary basins and upper crust, working on both more academic and oil industry related topics. His main areas of expertise are structural and tectonic development of reef system, particularly East Africa and Southeast Asia, structural characteristics of gravity-driven deformations, tectonics and structural deepwater fold and thrust belts, and shale tectonics. He is a specialist in seismic interpretation of structurally complex areas, geological framework, paleogeographic reconstructions, section balancing, and the geology of Southeast Asia. And he published more than 210 peer-reviewed articles. The title of today's talk is A Giant Mud Canopy System, the North Sabah-Pagasa Wedge, Northwest Borneo, and comparison with the salt canopy. This seminar will be 1 hour long, including a 45 to 50-minute presentation and a 10 to 15 minutes audience question section. Welcome, Dr. Morley. We're very happy to have you here.
Okay, thanks very much for the introduction. And well, it's really thanks to COVID, I think, that we discovered that Zoom can be so useful in international seminars. Certainly before COVID, I don't think I would have been able to have this sort of, or people think about having this sort of long distance meeting. As you can tell from the introduction, I am a structural geologist, not a geophysicist. So you're going to get geophysical interpretation in this talk, not much hardcore geophysics. Now, I need to be able to share this.
Sure.
I'm disabled from sharing at the moment by the host.
Okay, my co-host. I think you'll be able to share now.
Okay, yeah. So can you see my screen?
Yes.
Okay.
Yes, I can.
So here's just a few random images of the area. I won't explain them at the moment, but you can already formulate some opinions on what they might represent. This talk is based on, largely based on this paper. It's one of the last things I was doing when I was working for PTT, and so I'm grateful to the company for enabling this to be published so I can give this talk, and to my co-authors here. The area that I'll be talking about today is from the island of Borneo, which is broken into 3 different countries: Indonesia, Malaysia, and Brunei. And the area of interest is up here in Sabah, and I'll be talking about the offshore area here. In the introduction, I'll talk about deep water fold and thrusts a bit, the tectonics of Borneo, and mud volcanoes. Then the seismic interpretation of the area, and then a bit of a wrap up with models for the development of the area, comparison with salt tectonics, and a summary. Okay, so first of all, we are looking at least in part, a gravity-driven system. Gravity-driven systems tend to occur where there's thick overpressured shales at the base of a sequence, and there can be sliding on these either due to the dip of the basal detachment or due to sediment loading or a combination of the two. They behave like giant landslides, so there is a region of up-dip extension, a zone of translation, and then in the toe region, there's a region of compression, which usually involves folding and thrusting. And it can be on a fairly narrow detachment or quite a thick detachment, as is the case in the Mexican ridges. These can be very large systems, as in the Amazon fan here, with a scale of 40 kilometers, or much smaller systems, such as this example from the Indian margin. There can be diapiric shales, or shales that have been interpreted as being diapiric, or they can just be simple translation without much mobilization of the shales. This example from the Orange Delta in South Africa. Of course, you're close to a very large province in the Gulf of Mexico that's driven by gravity, where there is both the involvement of salt tectonics, very importantly, and to a secondary degree, there's shale detachments within the system too. And there's this very large salt canopy, the Sigsbee Escarpment, out in the deep water part of the Gulf of Mexico. It's been very important for the deep water discoveries in the area, and also for advancing geophysical techniques to be able to image below the salt basin. So the salt has climbed up from where it was deposited within the Jurassic up through the Cenozoic sequences, and is now at or close to the seafloor. So we'll come back to this a bit later. So this is where the concept of salt canopies was initiated, where diapirs from numerous locations rise through the section and then coalesce shallow in the section. Although there's a lot of similarity between gravity-driven systems and salt-driven systems, there are differences because of the material behavior of the two key detaching units. Shale is largely driven because of overpressures, and when fluids leave the shale, it becomes stronger, whilst the weakness of salt is a fundamental material property that is not affected by things like overpressure. There is one system that's been proposed already as a mud canopy system, really only one in the world, apart from the one I'm going to talk about in Sabah, and that's the Nile Delta, came from a PhD thesis by Kirkham. And this is the Messinian salt, which is late Miocene salt in the Mediterranean, and overpressured fluids have gathered below the salt, and then they broke through and pierced the salt and then gathered as these mud flows above, and the mud flows have coalesced in some places to form a mud canopy system. And then there are mud volcano systems that are continued, not as large volume, that go all the way to the surface. So these Small dots represent the mud volcanoes. These red and blue areas represent the coalesced, deeper mud volcano systems. And I'll be showing you something somewhat similar in Sabah, except there's no salt involved in Sabah. We can think of deep water fold and thrust belts as developing in three different ways, with two basic end members. One are the gravity-driven systems in deltas, near field stress systems with up-dip extension, down-dip contraction. And in these systems, the stress is here. The long axis represents the maximum horizontal principal stress, short axis minimum horizontal principal stress. So the stresses will be parallel to the growth faults, the extensional faults in the proximal position, and they'll be perpendicular to the compressional features in the down dip compressional toe area. In far field stress systems, we don't see the up dip extension. Everywhere we have thrusts in accretionary prisms, for example, and the stress system will be dominated by a compressional stress orientation. We can also have some mixed systems where there's a combination of lithospheric stresses, far field stresses, and gravity-driven stresses, in which case we may see stresses orthogonal to the thrusts down dip, maximum horizontal stress parallel to extensional faults where the extensional faults are active. Then coming back onto the near shore area, we flip back to the maximum horizontal stress being perpendicular to the structures. And this is what we see offshore Northwest Borneo. So this is Brunei here, Sabah up here, gravity-driven system here, the Barham Delta. In the near shore, we see these stresses in this orientation. And there's inversion of the growth faults in this region. Then in a narrow strip near the shelf, we flip around to stresses parallel to the normal faults. And then in the deep water area, the stresses are perpendicular to the structures again. So quite a complex system in Northwest Borneo. Just to show you the regional setting, here is Borneo, South China Sea, an area of predominantly Oligocene and Early Miocene seafloor spreading here. The island of Palawan in the Philippines to the north, I'll be referring to that a little bit, and mainland Indochina, Thailand, Myanmar, Cambodia, Vietnam, Malaysia, Indonesia here. Surrounding the island of Borneo, there are a number of basins that have been highly productive for hydrocarbons. They're Miocene to recent in age. And these orange areas denote deep water fold and thrust belts that are present. And then up dip, there are these extensional gravity-driven provinces. Just in terms of scale, the island of Borneo is about just a bit larger than the state of Texas. Okay, so the tectonic setting. As I indicate here, there's a lot of controversies about what I'm going to say, and I could talk for at least an hour just over why the tectonic model I'm going to give you may or may not work. But it's not that critical to the story I'm telling today, so I will give you the standard tectonic model as it's currently understood, but all aspects of it may be subject to revision in the future. So this map here, present day, shows dark blue areas, regions of oceanic crust, lighter blue areas, areas of extended continental crust that are currently marine. The light yellow is coastal deposits, and the brown are highlands. So this is the island of Borneo. And from the Miocene to the recent, we've had seafloor spreading in the South China Sea that has propagated to the west with time, and that stopped in the early Miocene. This extension was accompanied by driving this area of thin crust, the dangerous grounds, to the south. There's a subduction zone along this trend, and this hypothetical, possibly imaged on mantle tomography, area of oceanic crust, the Proto-South China Sea, was subducted below Palawan and Northwest Borneo, and you see this disappearing, and by the Middle Miocene, it's gone. And so there was collision between the thinned continental crust of the dangerous grounds and Borneo. And this ended by about the Middle Miocene. Northern Borneo was an area of marine deposition into the Oligocene, and then you'll see the propagation of subaerial land surfaces into this area as Borneo uplifted as a result of the collision, possibly as a result of delamination of the mantle lithosphere. So we had this uplift, and that triggered erosion and the deposition of these deltaic systems around the margins of Borneo. There's been quite a long history of seismic investigation of this margin, beginning with the German Geological Survey, geophysical surveys offshore Northwest Borneo, which was published in '89. You see the seismic data is not that wonderful, but you can make out this deep reflection here. And there's something that looks like an accretionary prism, but is not here. And the interpretation is that we have these thrust systems with this sedimentary section sitting above the North Palawan terrain, which I refer to as the dangerous grounds. And they identified a region where you could see folds and thrusts very clearly, and a region where they were not so apparent. This 4 area here. Today we have a lot more seismic coverage of the area, much better resolution, so we can see this area a lot better. So you can see clearly that there is a wedge between this very strong reflection here that corresponds with the Nido limestone, which is the top of the dangerous grounds crust. There's Sin Rift section below it, the continental basement. And then this sedimentary section above, and then this wedge is capped by late Miocene deposits. So we can track the wedge. This just shows its thickness from 0 to 5.7 seconds two-way travel time thickness. So it becomes a very thick wedge in places. And this regional section here just shows the morphology of it. Generally, it's pretty chaotic within the wedge, except in the frontal areas where we can see more features. And we see this Nido limestone here dipping back below, and then eventually it gets too deep. So this line splits, the south is here, north is here. but it's one of the best deep lines down to 12 seconds. There's some reflectivity here at around 10 seconds that could be the moho. That's about the right depth for the moho. And then we've got this wedge sitting on top of the dangerous grounds with the Sinriff section here, predominantly Paleogene age, being under thrust below. Looking at the wedge a bit more, we can just zoom in and see that there are features that look like it's imbricated, so we can imagine there are thrusts in here repeating the section. There are also mass transport complexes within it. And then zooming in some more, you can more clearly see the imbricated nature of it. And clearly the undeformed sediments sitting over the top of it and the Nido limestone at the base. It's been drilled by some wells. This is going up north of Borneo now to Palawan, where the wedge continues. And the wells that have been drilled into it show the lithology, few limestones, but predominantly siltstone and claystone with some thin sands. And the age of the wedge is Middle Miocene to Eocene. And the Eocene's presumably from the lower plate slices that have been incorporated into the wedge. Okay, so this diagram shows a few key features of the system we'll be looking at in Sabah. So in brown, there are these Middle Miocene mini-basins. So this is when the deltaic sediments of this uplifting land have been shed off onto the margin. They've loaded the margin and they form these rather unusual, strange-looking synformal depicenters. And between there are these more chaotic uplifted areas that are inferred to be mobile shales. So overpressured shales that have been mobilized as a result of the sediment loading. And this continues into this area, block H, which is what I'll be talking about. And here, this is the wedge that I've been showing you. And you see there's a lateral change to a different color. This wedge is older and it's much more poorly imaged. This wedge is younger and it's just a classic late Miocene to recent deep water fold and thrust belt. So there is this boundary here between the two, that is this boundary here. And there are mini basins sitting on top of this wedge that I've been describing. So a cross-section through this area shows the wedge. It's poorly imaged, shale-dominated, overpressured wedge with these mini basins in orange. And then the mini basin formation stopped and a more regional coverage of sediment with less deformation covers this whole thing. And this in turn is sitting on an older wedge that can be interpreted as an increationary prism that's a Paleogene age. Kudat wedge or the Crocker wedge, depending upon where you are along the margin. Kudat wedge is up here, the Crocker wedge is down here. This is a stratigraphic section. So this older part, the Eocene-Oligocene, either corresponds with the dangerous grounds crust that's being underthrust here, or the Crocker wedge, which is, or Kudat wedge that's sitting in here. We then have the Pagasa wedge sitting on top, the mini basins that are of Middle Miocene age to early Late Miocene. And then what I'll be talking about is just sitting on top of this is a mud canopy basin. So at the end of this sequence, I'll eventually get around to showing you examples of mud volcanoes that occur here. So they occur right at this boundary between the mini basin and the mud canopy basin. And then we have just this aggradational basin sitting on top. So what do the wedge sediments look like? Well, we get to see on this island here, so we've been looking up here, but down here we've got an island where early Miocene sediments are exposed. They're shale dominated with a few thin sands. They look like this in outcrop. There are some fluke marks on them. There are also more trace fossils. So predominantly shale, but with some silts and sandstones in the sequence. There's quite a few wells through the area. So this would be the North Sabah-Pagasa Wedge, seismically transparent. Unconformably sitting on top is this mud canopy basin, which in places has thick turbidite sands. Here, 78.5 meters of net sand, 94% net to gross, very good average porosity, so a very attractive reservoir. But you can see this unit thickens and thins a lot. So just within this small seismic section, this is 1 kilometer, there's a lot of lateral variation within this sequence due to the nature of the mud canopy basin. There's also a very nice strong reflection here that is a gas-water contact. I mentioned that we've got 2 adjacent deep water fold and thrust belts that are very different. So these are just 2 sections showing the difference. We've seen this section before. This is the section to the south, and you can see here the seafloor is folded, so deformations continued up to the present. You only get that in the external part of this zone. And you can image, at least in the external part, all the way down to the wedge. There's no really mobile shale. It's all just folded and thrusted by this late deformation. So what we see in this wedge is earlier and just very different from what we see to the southwest. And this is the boundary between the two, where we have the shale-dominated wedge here, over thrusting this wedge here. Okay, on to mud volcanoes a bit, just in case you're not familiar with the morphology of mud volcanoes. The area in the world that's got the largest subaerial mud volcanoes is Azerbaijan, here on the west side of the Caspian Sea. The mud volcano deposits overlie geological units in this area, so we can see the thickness of the extruded mud, and it's 200 to 400 meters thick. Individual mud volcano vents shown by these red arrows can be clustered along a ridge, or they can be isolated large mud volcanoes, as you see here. So there's quite a variety to the distribution. Now imagine this kind of province erupting in a deep water setting, and that's what I hope to describe to you in Sabah. When we look at these mud volcanoes, they can form tongue-like flows. So this is 200 meters wide and 2.3 kilometers long. There can be central vents, and then we have these concentric ridges and troughs in the mud flows around it. There can be blocks in the mud flows. And the way these mud volcanoes erupt, they can be quiet for long periods, then there's an eruption, then the activity dies off. Pressure builds up in the subsurface, and eventually there's another eruption. And the time between these eruption episodes can be somewhere in the order of 5 to 100 years. There's a tremendous amount of gas that gets erupted with these. And in Azerbaijan, it can be very spectacular, the amount of gas and the gas burning off associated with these large mud volcanoes. I won't read this out, but you can see the numbers here indicating the very large volumes, millions of cubic meters of gas and mud being erupted from these large mud volcanoes. The model for how these mud volcanoes develop in Azerbaijan is one where you have fluids, gas-rich, hydrocarbon-rich, particularly in methane, being derived from deep source rocks. The geothermal gradient is low here. So this can be 9, 10, 11 kilometers depth. So the fluids come up and then they mix with muds from a much shallower depth, typically 2 to 3 kilometers. And then these two sources mix and rise up together to give the surface mud volcano. From the Niger Delta, there's some nice seismic images of mud volcanoes, shallow mud volcanoes, and they tend to have this morphology. There is a sag, and this sag is developed due to fluids and mud being depleted in the region below. So there's volume loss and there's this informal sag, and then the mud volcano builds up in this depression. And then as the mud volcano progresses, it rises, it can rise through the section as there's deposition and give rise to some quite complex geometries. Trinidad is another area where there's a lot of mud volcanoes. This geometry is established by a lot of drilling as well as seismic data. There are sands that are sealed against the mud volcanoes that contain oil. And we get this, what's called a Christmas tree type pattern, as this is called a mud chamber here, but it could be a series of mud volcanoes that has just risen through the section. So we're not sure whether there are mud chambers just like there are magma chambers for volcanic eruptions, or whether there's just a pipe and then an accumulation of mud flows that give a chamber-like appearance when those mud flows get buried by subsequent sedimentation. Okay, so now that's the end of the introduction. This is the seismic data from the upper part of the section in Northwest Sabah. This is pre-stacked, time-migrated 3D seismic data. You can read the acquisition parameters if you're interested. This is zero phase, standard SEG polarity. Black is a peak, red is a trough. This is from the northern part of the study area. And you can clearly see the pipe-like nature of fluids escaping to the surface here. And then there are other mud volcanoes that have stalled in the subsurface. They're older and have not grown to the surface. And so we get this build-up over the synformal geometry, just like the Niger Delta examples. So these are clearly mud volcanoes that are growing in the shallow subsurface of the Sabah area. So we know we've got overpressured shale conditions. We know that there are some mud volcanoes present. Another shallow example is this one. It doesn't have so much of the Christmas tree pattern. Looks like a mud chamber, but again, is it actually just a series of mud flows that have amalgamated. And we can use the sweetness attribute to map out geobodies that define this feature. Now, I was trying to describe these things, and one description I thought of was a walnut whip, and it's the best and only description I can. Unfortunately, walnut whips are well known in the UK, but they're not so well known in the rest of the world. So it is, I think, a great description. Unfortunately, it can't be used internationally to describe these things. And the Christmas variation of this walnut whip is even better because you have the feeder to the mud volcano featured in this example, as well as the deep source area down here somewhere. Okay, so this map shows the Block H area. There's a North Block H and the South Block H, and I'll be showing examples from both. The gray shows the mini-basins, these informal basins that laterally pass into these chaotic areas that are assumed to be mobile shales. And in red or pink are these shallow pipes and mud volcanoes, and in blue are the deeper ones. And I'll show you some lines that will explain this better. So I'll be using these as the location maps for the examples that I'm showing you. So first of all, in the north, this is the seafloor map. You see there are a number of channels on the slope going down to a more gently dipping area that is not so channelized. These are the shallow mud volcano features. There are also a lot of shallow faults, small minor faults that affect this area, but they're not really related to the mud volcanism. And then as we go deeper in the area, we see the mini basins on this time slice at 2.5 seconds. And these are the deeper mud flow systems that cover a very large part of this area. Okay, so here's a strike line parallel to the slope that shows these two systems. You've got the shallow mud volcano systems here and gas chimneys. These shallow faults that I was showing earlier occur up here, and these are the channels in the slope. And as we go deeper, we lose the channels. And then the system that I'm most focused on is this one. This is the mud canopy basin, and below that is the North Sabah-Pagasa Wedge. And I've drawn in this blue color here the mud volcano systems that are intrusive and extrusive complexes, amalgamated mud flows. And this takes some imagination. You can certainly challenge the interpretation in places, but you do see hints of it. You've got these transparent features, but there's strong amplitudes in here. There are these peculiar looking geometries in here. And then you've got these very strong reflections in here that are coming often from the turbidite sands that I showed you in the well that have very good reservoir quality. So this is the mud canopy basin sitting in here, and it goes from these strong reflections into these very transparent reflections, which are probably related to mud flows. So we get to see some very strange looking bodies here surrounded by high amplitude reflections, and then are chaotic in the interior, and they cross cut the surrounding reflections. But in places there is stronger reflectivity within these bodies. They look like mass transport complexes. And in many cases, that's what they were originally interpreted as. But as you can see from these more Christmas tree-like geometries here, here's the sketched interpretation. These transparent bodies look a lot more like mud volcanoes. So if these are mud volcano-related deposits, then why are these not mud volcano deposits than these? Now, one peculiarity here is that you see the reversal in the polarity from the upper surface, black to red to black. So clearly telling you there is a change in velocity within this unit compared with the surrounding sediments. These are quite shallow, and they're low density sediments with a high water content, can be up to 70% shallow. Now, mud volcanoes in Trinidad, surprisingly, seem to dewater quite rapidly. And their average water content is 34.5%. As I mentioned, the background sediments have very high water content. So actually, the mud volcano deposits may have a lower water content than the surrounding sediments. So they're actually higher velocity. They're both quite slow. But if we model these geometries with the sediments having velocities of 1,600 to 1,800 meters per second, and the velocities of these bodies having 1,700 to 2,000 meters per second, they're relatively hard. In these synthetic seismograms here, red is positive. In the actual examples, black is positive. We create a very similar morphology to these by having the mud volcano deposits as being a bit faster than the surrounding sediments. And so that's what we see in these geometries. This system mapped the bottom surface and the upper surface. It's very irregular, so it's difficult to map. But this is what it looks like. So that's the base. This is the isochron map, and this is the top. We can see a feeder pipe at the bottom, and there's a shallow pipe that's emerging from the top. So this is a mud body that grew by multiple flows. There were periods of quiescence, so the background sediment gets deposited into the wedge, and then more mud flows come over the top, more sediment is deposited. So we get these strong reflections in places within the wedge. There's a mud pipe growing through the wedge, and it's presumably feeding over pressures into the wedge, so this wedge can become remobilized and lose some of the reflective boundaries within it as a result of the wedge becoming remobilized, and it flows, and we get to see these imbricated systems as this has been remobilized later. And then finally it gets covered by sediments. And these ridge-like features are reminiscent of the ridges and troughs that we see in the Azerbaijan mud volcanoes. This is just an example of cross-section profiles through some of these mud bodies at a 1-to-1 scale. We're looking at time sections usually, so it's useful to see what they actually look like at 1-to-1 scale. Okay, so here again is this mud canopy basin, and you can see this is from Northern Block H. And you can see these continuous reflections, and then they pass into these chaotic units. And so the interpretation is that there are these coalesced mud volcano systems in here, sitting over the mini basins. And that we can try and map these things out and identify some boundaries between different mud volcano centers, which is what these blue polygons represent, these different bodies. It's not certain. This time slice and vertical slice section through the 3D shows that there are sort of hints of boundaries within this chaotic unit. And so maybe you can divide this up into different mud volcano centers. In places, you do get to see the tops and the bottoms of these very clearly, but that is quite rare. In some places, you also get to see the feeder pipes, a mud volcano complex, and then another one developed above it. So different stages of development. And then in the mud canopy section sitting on top, there are these extensional faults, predominantly gravity driven, but there are a lot of odd orientations to some of these faults that are not typical for gravity-driven systems. And these normal faults seem to be developing where there's mud volcanoes below. Here's one. So possibly they're interacting with the vent systems and they're collapsing on the vents, giving rise to some odd orientations of the faults. And again, notice how this mud canopy basin here with these strong reflections, they terminate against mud volcanoes that have risen at the same time that they're being deposited. They pass laterally into these transparent systems that may be mud flows. Okay, coming to the southern area now. We're again right at the transition here between that southern, well-imaged fold and thrust belt and the North Sabah-Pagasa Wedge with the mini basins and the loaded shales. And right at this thrust front, there's a real complex of transparent units with the occasional reflection that are interpreted as stacked mud flows. So just take a closer look at this external system here, where you can see the strong reflections, the chaotic areas in between, and we can interpret different mud flows sourced from different pipes at depth. So here I'll just run through a series of cross sections so you can see the change in morphology. We have a late fold here. There are another late fold here. Here we start to lose some of these systems. This one's persistent, this one starts to come in. We see some imbricate thrusts here. Now this system here is developed pretty well. There's a gas chimney and a probable feeder here. We can see these systems interfingering. And in this one, you notice there's a nice flat spot that's trapped by these, so it's gas trapped by these overlying mud flows. Okay, so let's take a look at the development of one mini basin up here, the Tanjung mini basin. So this is predominantly Middle Miocene with Late Miocene sitting over the top. If we look at the geometries of the strata here, the lowest strata seem to deform in a sort of sag-like basin, no fault control. The next horizon, fairly constant thickness. And then the next horizon, this one is controlled by a growth fault. And then there's a period of inversion and thrusting. So we have compression, which ends this mini basin, and immediately following this compression, we have a period of erosion, regular surface is set up, and then the mud flows occur, and they start to fill in this irregular surface. And then the mud canopy basin sediments, the turbidite sands, are deposited over the top of that. And we have a bit more mud volcano activity at this time. Looking in a bit more detail, same basin, this is the mud canopy section. You can see that there are different geometries within this section as the irregularities of this post-inversion stage and the mud volcano stage are being infilled. We have this early mud volcano at the base of the sequence, mud volcano sequence. This is the canopy. But in places, the mud volcano system continues after. So this box here just shows the seismic in this area, and this box here shows the seismic in this area. So you can clearly see the mud canopy system here and the mud volcano system growing here, and the earlier mud canopy system here and the slightly later one sitting in here. After we did this study, the company made a pre-stacked depth migrated velocity cube, which shows some nice things. So this is interval velocity. Red to brown is high interval velocities. These are very low interval velocities, 1,500. But you notice, okay, the seafloor's dipping a bit. So this is a shallower depth in the subsurface than this area. But nevertheless, approximately equivalent. We have the highest velocities here in this mini basin area, as you'd expect, where you're burying sediments. But laterally, we go into some of the lowest velocities. And so these pockets of low velocity, we assume are water-rich, undercompacted sediments that would be mobile shales that could source the mud volcanoes. So it's very nice imaging here. When we look at the strike section to this, we really get to see the morphology of these low velocity areas, which are at about 4 to 5 kilometers depth. The seafloor here is about 1.5 kilometers. So in the subsurface here, we're looking at 2.5, 3 kilometers, 4 kilometers depth here. So these look like they're being loaded, squeezed out here, rising up here, and there are, in salt tectonics, we call these welds here. It looks like these are shale tectonic welds as materials being squeezed out here. Okay, so mobile shales. Their properties change with depth. They're mobile because of their fluid content. They can also be mobile because shales are weak minerals. Clay, the clay fraction is weak too. But they change as a result of burial, pressure, porosity, permeability, lithology, thermal conductivity. There's a whole range of factors that influence how shales behave. As we bury a shale in the subsurface, we go from mechanical compaction being the dominant effect, particularly shallow, where we get expulsion of free water, to chemical reactions as temperatures increase and we start converting clay minerals to different clay minerals, for example, the smectite-illite transition. We can have overpressures generated as a result of disequilibrium compaction, which is just overpressuring mechanically due to burial and pore fluids not escaping, so the rock ceases to compact. But also chemical changes can expel water from the lattice of the clay minerals, and that will create overpressures too. So this shows the rock type, plastic clay to shale to slate, as we bury the rocks and the temperatures get higher. The burial effects, we go from smectite to illite, for example. Chlorite can appear, graphite can appear at much greater depths. We go from oil generation to gas generation as we get deeper. And as a result of the changing rock properties, the structural style will also change. We go from a plastic mud to a rock that may undergo pressure solution deformation that will develop graphitic slip surfaces at depth. And this transition from around 90 to 120 degrees is very important for strengthening the rock because diagenetic silica starts to stiffen the mud rocks. And this diagenetic silica gets precipitated in the smectite-illite transition. So if we take a seismic section and we estimate the geothermal gradient, this 100-degree centigrade line here suggests where we go from more plastic mud to stronger shale. This is the top of the wedge at the moment. So much of the shale within the wedge now is probably quite strong and will not readily, well, fairly readily it will deform, but not deform as readily as it did in the past. When we remove this overburden, then we can see that the upper part of the wedge with the overburden removed, so earlier in the burial history, would still be very weak. So it's important to remember that there's this burial that affects shale sequences, unlike a salt-driven section, and that the deformation in in the shale can migrate upwards with time, as the upper part of the shale stack will be weaker than the deeper part. So looking at the evolution of the depicenters and following this Azerbaijan example, we have the lower part of the North Sabah-Pagasa Wedge in the gas window, contributing fluids to a shallower, weak mud layer that gets loaded by the mini-basins, and it flows and moves. When the basin inverts at this stage, something extra happens to this system. In extension, when we look at a depth pressure plot and the values of the principal stresses, we get hydraulic fracturing and escape of overpressured fluids when the pore fluid pressure reaches the value of the minimum principal stress value. In extension, the minimum principal stress is horizontal, so it will be less than the lithostatic pressure, often about 0.7 to 0.8 of the lithostatic. When we have that phase of compression, then the minimum principal stress is the vertical stress. So the minimum principal stress is the lithostatic pressure. That's this one, this stage, which enables the pore fluid pressures to be higher, to equal about 1, which is the lithostatic pressure, than they were in the extensional stress state. So during compression, the pore fluid pressures can become larger. When that compression ends, the system relaxes back to the state where the minimum principal stress is horizontal. So it wants to go back to this early state. That means the overpressures here are too high. They'll fracture rapidly. And so that can result in the rapid expulsion of lots of mud, the mud volcano activity, to the surface all in one go, right at the end of this compressional activity. So we have this burst of mud volcano activity giving rise to the mud canopy, and then the system's relaxed, it's driven off a lot of the overpressure, and we get the mud canopy basin developed on top. So that's quite different from salt canopies. This is an oblique view of the Sigsbee Escarpment. We see the salt in the near surface and these mini basins developed on top. So this example of the Gulf of Mexico example, we have salt rising as diapirs, we create the mini basins. So this is fairly similar to what we're looking at in the Sabah example. But then the salt coalesces at the surface, it forms this sheet, almost complete evacuation of the salt from the lower layer to the surface. Then this gets reloaded and we create a whole series of mini basins above, like these features. The mud canopy never reaches this stage. It really stalls at about this point. So when we look at this cross section, we see elements of this cross section. This area looks quite like this area, but there's not the lateral translation that we see here, and there's just not this late reactivation and reloading. So this just shows the general evolution. We have the wedge loading by the mini basins, the expulsion of the mud volcanoes at the end of a phase of compression, then they get covered and the system quietens down. There's a little bit of gravity reactivation, but that's it. So we can summarize the system as having a gas generating area deep. The fluids from the gas generating area reach a shallower mobile shale, which we image on the velocity cube. There are pipes, possibly mud chambers. We don't know really whether mud chambers exist or if they're just buried mud volcanoes that rise to this canopy, mud canopy section of coalesced mud volcanoes. So this intense burst of mud volcano activity, deposition of the canopy system, and then some continued mud volcano activity shallow in the section, but much reduced from this stage. The mud canopy stage in many ways resembles a deep water fold and thrust belt system. We have slope channels coming in, which can be feeding in turbidite sands. When the turbidites exit these channel systems, they expand and they flow into the areas of lowest topography. They're influenced by the topography of thrust-related folds, but also in the case of the mud canopy basin that's sitting on top of these mini-basins, we have mud edifices that are also creating high areas that influence where the sands cannot or cannot go. We have these inverted mini-basins that have these circular geometries. So rather than just the linear fold and thrust belts, we have these lateral folds as well that interrupt the flow. And then there are remnant eroded mud volcano edifices poking through in places. So there's quite a complex environment that concentrates the sands in particular areas in this deep water basin. So in summary, this area that I've described is one of the few, so it's easy to be the largest known deep water mud canopy in the system. It covers a large area, about 3,500 kilometers square, and the areas of the dense mud canopies total about 1,900 square kilometers. There are some similarities to salt canopies, but the different deformation mechanisms mean that mud is much less likely to remigrate when sediments load the system later. We see some of the same topographic elements that classic deep water fold thrust belts have, but there are extra elements as well, these inverted mini basins and the mud volcano remnant topography. And there's also these extensional collapse features. So this makes it an unusual depositional environment for turbidite reservoirs and some of their trapping configurations. It's a bit more complex than typical deep water systems. The seismic amplitude characteristics velocity data indicate that these mud intrusive extrusive complexes may be predominantly derived from mud flows, but can be augmented by mud intrusions. And we see things that look like mud chambers, but they may actually just be modified mud volcano edifices. And what caused this massive mud volcanism in a short period of time? I think the answer is stress release after a phase of compression. So thank you for your attention. And that's it for the presentation. I'll happily take questions.
Thank you, Dr. Morley. So we have our time, but we'll take a few questions. So Anyone had questions, please ask.
Yeah, can I ask a question?
Sure.
Very interesting phenomena. So when you say these are mobile shale or salt, they start to move in the form of volcano. Can we estimate their strength if we treat them as a viscous fluid, for instance? Then, in terms of viscosity, do you have an estimate how weak they are?
I think very weak, because they're, from those velocity estimates, they're probably 40% water at least. Maybe in some cases there's a lot more.
So not much different from the water viscosity itself, would you say?
Yeah, they have to flow a bit slower, but yeah.
Okay. And in the summary slide, different deformation mechanisms are being mentioned, but fortunately, I don't remember the specific information given earlier.
Well, so salt behaves very consistently over a variety of depths. And it's an intrinsic property of the rock, right? But with shale, its ability to flow depends on its water content. So as it gets buried, it becomes less plastic. You could drive off most of the water and still the shale would be weak, but it would be weak for a different reason, because the clay minerals are weak. And if you heat up the shale enough, then you may get graphite forming, and then graphite is particularly weak compared with other clay minerals. So it's highly variable how shale will behave depending upon burial.
Last question then, can we say in general, this mobile shale would be much weaker than salt? Can we say
No,
that?
it's the other way, generally.
The other way.
Yeah, maybe if you have a highly water-rich plastic mud, it would be weaker than salt, right? But as it gets buried, it rapidly flips the other way around, that salt is weaker than shale.
Oh, okay. So at depth, right. So if it's not fully saturated with fluid,
yeah, if you've got the mud flow, that's weaker than salt. But
yeah.
Yeah.
Thank you.
Any more questions?
Yeah, I have a question. Go ahead.
Hi, yeah.
Okay. Thank you for this presentation. This is actually the first time I saw in your previous slides the Niger Delta. I know that's a basin in the southern part of Nigeria. I didn't know we had mud volcanoes there. Is that offshore or onshore?
No, that was the Nile Delta. Oh, I know the one you mean. Sorry. Yeah. There's lots of mud volcano activity, and there's some big potential shale diapirs in the upper slope of the Niger Delta. Yeah, there's a lot of shale tectonics in the Niger Delta.
My question is, like, is it offshore, like in the deep waters, or was this observed in the onshore area?
Well, onshore you've got the growth faults, so underlying it there will be a shale detachment, but you really get to see the main shale bodies in the outer shelf slope area. And then there's some very good examples.
Okay, thank you.
I have one question. I may have missed it when you were describing
background geology in the front of the presentation, but was this area ever a convergence zone? Was there thrusting of oceanic plates underneath it?
Well, that's a good question. Yeah, the standard tectonic model is yes. There are some people who dispute that. But the standard model is the Proto-South China Sea oceanic crust was subducted below Northern Sabah. And then in the Early Miocene, the dangerous grounds, thinned continental crust entered the subduction zone and jammed it. But that's still quite thin continental crust, maybe 10 kilometers. So it's not thick enough to make that deep water area emergent. So you have the Crocker and Kudat formations that are the accretionary prism, and then you've got this sort of post-collisional wedge sitting on top. That's the North Sabah-Pagasa Wedge.
Oh, I was wondering if large earthquakes could shake the mud volcanoes loose.
There's very little seismic activity. There is a bit, but not very much in Borneo. So maybe in the past it could have done it. Maybe for that one burst of activity, it could be you had some seismic episode that did it. But yeah, I don't know how you would be able to demonstrate that. And it is a bit late in the development to expect much seismic activity.
Okay, thank you.
So I think, is there any more questions?
I have one question. So are these of different viscosities, or all of them are of the same viscosity, the mud volcanoes?
Well, probably the mud volcanoes are fairly similar, although they do vary. Actually, they do vary themselves. There are some, if you look at mud volcanoes in different parts of the world, some of them have a high water content, 70% or more. Most of them don't. The Trinidad example I gave is a better average where it's lower. But even within that Trinidad example, some of them were very low, others were quite high in their water content. You know, I think 20 to 30% versus 60 to 70%. So it is highly variable within provinces, between provinces.
And 20 to 30% of water content is like a lower limit to half of mud volcano.
Yeah. There's a lot of methane in these things, very high gas content. But they degas quite rapidly. So that's probably one of the problems with measuring them. You can measure them just as they emerge on the surface and try and get a good reading. But if you measure them a bit afterwards, they will have degassed and dewatered. And they do it quite rapidly.
Okay, thank you.
Okay, if there is no question, I think it is a good time to stop. Thank you, Dr. Chris Morley, for joining us. It was a very nice talk. And thank you, everyone, for joining this seminar.
Thank you.
Pleasure.
Thank you.
Thank you for your attention and questions.
Thank you, Chris.
Bye.